Okay, good morning to all of you. Today we will discuss the part 2 of the transport layer. Already in the previous video we discussed about the different functionalities like process to process communication. We discussed about the functionality about reliability, connection oriented services, connection less services. So one of the functionality is called flow control. In addition to that, other flow functionality include congestion and error control. So today's video will be focused on the transport layer flow control mechanism. So in general, in simple, flow control means that is what is the amount of information the sender can send without getting the receiver's acknowledgement, and basically what the significant of the flow control is determine the channel utilization. So if the flow control is select the best appropriate protocol, then the throughput, end-to-end delay, other parameters in the networking parameter point of view will be better. In other way, if this not correctly communicated or not correctly set, the adverse effect like packet loss, congestion, other things can happen. So this plays a major role for networking protocol. So we have to discuss the flow control by starting and discussing with a simplest protocol, and gradually we will add more complexity, and we will start onwards like stop and wait, followed by GBN, and followed by the selective repeat. Before discussing the flow control, let's start with a simple, here it is referred as simple protocol, but actually in order to make the understanding better, we will discuss the protocol as a simple protocol, where it is assumed that this protocol does not have any flow control mechanism, and it is a simple connectionless protocol like UDP functionalities. So quickly, the way it is encapsulation is done: once it receives the message from the application layer, and then transport layer puts the packet number and then send to the receiver. Receiving transport layer receive this, and this receiver transport layer receives and then make the decapsulation, and the application process receive this. So it doesn't consider any window concept here, as well as no flow and error control mechanism. So this is simple protocol, how a packetization done in a transport layer, and it will deals with only one state, ready state. Other state will discuss subsequently for the corresponding flow control mechanism. Just a request come from the application layer, it make a packet and send it, and this is the ready state in the sender side. And once packet is arrived, delivering the process to delivering the packet to appropriate process is done by the receiver. So this is the simple protocol. Now make some uh, complexity to this by discussing the that is the first protocol, that is called stop and wait. Stop and wait protocol is a connection oriented protocol which include both flow and error control. The sender will set the window size, that is a sliding window of size 1, and the receiver also set the window size equal to 1. That is the basic simplicity in case of stop and wait. What the parameter it uses, what one it uses a sequence number, but that is 1 bit in this stop and wait. Also the acknowledgement is always higher, one value higher than the sequence number, and the state transition we have to discussing the sender action and receiver action. And the one of the major limitation is its efficiency, because it is not fully utilized. Channel capacity or channel utilization is less. That's the reason for which we will move to other protocol under this category. Let's start with the flow control at stop and wait protocol. Similar to the simple protocol, just we focus before just few minutes. Here it maintain a window, that is sending window with value 1, and there is a receiver window with value 1. So S is the packet number initiated by the sender, and R is the packet expected by the receiver. So initially when application process receive a packet, it make the packetization by putting the packet sequence number to S and send the packet, and it is transport layer received the packet only if the value matches as per the receiving window size. So for example, if packet number is 1, then receiver is expecting that 1. So it will be, if it is match, then you will receive and it will slide to next value. And here the value are in modulo 2 arithmetic numbered with modulo 2 arithmetic. That means the packet 0 will be numbered as 0, packet 1 will be numbered as 1, and packet 2 will be numbered as 2 mod 2, that will be 0. So 0 1 0 1 0 1, this way all the packets will be numbered in case of your stop and wait. Now coming to different states that in stop and wait. At receiver side, at sending side, there is a ready state and one is called blocking state. In the as well as in the receiving side, that is a ready state. So what the events takes place? First event is a request coming from the application, that is the first is application process prepare the message and that send the information to the application transport layer of the sender. Then transport layer make the packet and put the number equal to S, that you can say the initial sequence number, save a copy and send the packet and start a timer. That's the basic concept. It will number the packet and start the timer. And what the action it expect, and it enter to the block state. Once it send the packet, now it is in the block state, and in the block state what can happen, if timeout means if does not receive any acknowledgement within the time, you will restart the timer and resend the packet. If it received a correct acknowledgement, we can do the same thing. After the expiry of the timer, it will resend the packet and reset at the timer. And if you receive the error free acknowledgement, that means what? The packet is receive a correct acknowledgement, then it will slide the value of the next packet will be S plus 1. That is the logic in the sending side. In the same way, receiver, it received the error free packet with a packet number sequence number equal to R, then it will slide, delete the message to application and slide the value to R is equal to R plus 1. So if it is 1, 1 plus 1 is equal to 2, 2 mod 2 is equal to 0. And the acknowledgement will be R. That means the R means R plus 1 value. So if it receive the packet 1, then acknowledgement will be 0. If it receive the packet 0, the acknowledgement will be 1. So all arithmetic operations are in the modulo 2. That is the basic objective of the basic approach used in the stop and wait. And if a error free packet with sequence number R arrived, discard. That means if duplicate acknowledgement is received, it will discard it. That is a simple stop and wait protocol. But the problem in case stop and wait is that utilization of the channel capacity. Stop and wait protocol. Let's start before discussing the utilization with a simple example. The packet numbers are alternately 0 and 1. Already I have told why it is 0 and 1, because it uses arithmetic modulo 2 operation for the packeting number. So packet 0 followed by 1, packet 0 and followed by 1. So first packet a value of S is set to 0 and the R is expecting also 0. That means it is expecting 0, it receives 0. So when packet number 0 arrived at the receiver, it will match the value set available in R and it will send the acknowledgement slide to next value is equal to R is equal to R plus 1 mod 2. So R was 0, 0 plus 1 mod 2 is equal to 1. Now the value of R is equal to 1 and the acknowledgement is equal to your acknowledgement is equal to your R. What is the value assigned to R? That is your acknowledgement. So packet 0 acknowledgement will be 1, packet 1 acknowledgement will be 0, and so on. So this way the communication will be going on. So consider one example. One is called one packet. Next time when it receives the acknowledgement, it will send the next packet. Already it slides to 1. Now it send the packet 1, but it is lost. That means it is not delivered to the receiver and is receiver waiting for packet number 1, does not receive it by the time timeout event occur at this time. Timeout event means within the RTT round trip time, does not receive any acknowledgement. So after the expiry of the timer, then it say resend it. This is called retransmission occurring in case of your this stop and wait protocol is concerned. That means it resend the previous packet and once again run the timer. Same logic it will continue. So this is one scenario when the packet loss occur. Another scenario, if acknowledgement loss is maybe occur. Acknowledgement packet is delivered, means packet 0, it was expecting 0, received it, now it's slide to 1 and acknowledgement is set to 1, but this acknowledgement is lost. So what will happen? So when it is send the, it wait for the RTT, that is timeout, but does not receive any acknowledgement by that time, then it will resend it after the expiry of the timer. This way the stop and wait works. This is the basic working mechanism where we discuss a successful packet retransmission within RTT and acknowledgement. We discuss about the packet loss, so when the packet data packet lost, and we discuss about the acknowledgement packet loss. So in both cases there is a concept of retransmission, means there is packet is retransmitted again in order to achieve the reliability. Now coming to the limitation. Limitation is called the utilization of the channel, so link utilization, the major problem. So before that we have to discuss the issue, or we have to know the parameter called bandwidth delay product. In order to know the link utilization in a channel, then we have to compute the bandwidth delay, which determine what is the amount of data that can be delivered or can be sent between two systems with a given link capacity and with a known delay. So in this given example, it uses a stop and wait, means it sends only one packet, and that information is called given bandwidth of the link or line is 1 Mbps, and the RTT is given as 20 millisecond, means the time it takes to send and return back to the sender is 20 millisecond RTT, round trip time. Okay. And what is the, it is asking for bandwidth delay products. What is the bandwidth delay? So bandwidth is 1 Mbps and delay is 20 millisecond. So it is in second, it is in the millisecond, we have to multiply this. So this is in second, 1 into 10 to the 6, and we have to convert it to second. Millisecond means 10 to the minus 3. So it is plus 6 and minus 3, finally it is 20 to the 3, 20 to 10 to the 3, that is equal to 20,000 bits. So the bandwidth delay of this given example is 20,000 bits. We may convert it to bytes by dividing it by 8. That means the system can send 20,000 bits during the time. If the capacity, maximum capacity of this channel is 20,000 bits, but actually we are, how much we are sending? If the system data packets are 1000 bits, that means if the size of the data packet is 1000 bits, what is the utilization percentage in links? But we can able to send 20,000, but actually we are only sending 1000. So what is the link utilization? So link utilization is 1000 by 20,000, or it is 5%. So only 5% of the link we are utilizing. So this is the issue. That is the issue in the stop and wait. I think it is clear. Basically stop and wait suffer with the link utilization. So in order to improve this link utilization, the further protocol have to improve the sending capacity, and their flow, that is flow parameter, that is called sending window size, will be definitely definitely not 1. It may be higher than that, and that is the next protocol that we have to discuss. But before that, suppose the question is modified little bit. If the protocol send 15 packets before stopping and without worrying the acknowledgement. So in addition to the previous question, now rather than sending one packet, if it is continue for 15 packet, then utilization will be 75%, because in one packet it does 15%. So 15 into 5 is 75%. This way we can able to compute what is the bandwidth delay and what is the link capacity, and different numerically can be set by putting the different values for bandwidth delay as well as the packet size. We will discuss few things later. Now coming to the one of the most popular protocol under the flow control, that is called stop and wait. Sorry, this is called what? GBN, go back to N protocol. So what the definition says, it to improve the efficiency of the transmission multiple packet, must be transmission while the sender is waiting for acknowledgement. That means we can to send more number of packet when the RTT means within the round trip time or waiting for the acknowledgement. In this section, we will discuss one protocol that can achieve this goal, that is called GBN. We'll go back to the nth position. The objective is different, but before that, the parameter under the GBN is like stop and wait. It has a sequence number, but improvement is that it is number of bit is more, not one. So this is related. Number of bit used for sequence number is same as that of acknowledgement number. So if it is m bit, acknowledgement number will be also m bit. And we are using a two window. Previously we have used to sender window and receiver window. For value of the sender window and receiver window is always one. Means sender can send only one packet and receiver only recognize only one packet. And there is a timer similar to the previously one. And resending concept as well as lost packet and lost acknowledgement we will discuss. Okay. Definitely like your state transition and events, so we have to discuss at sender and receiver, and we have to compare the both protocols so far. That means the issue associated with stop and wait and what are the enhancement we achieve through GBN and what the issue exists which can be further improved through other protocols we will discuss later, and that is called select repeat. Now starts with understanding how this works. Now here if you know the above diagram already we discussed, sender receive the application process, prepare the message, then make the encapsulation here, put the application sequence number and send the packet. But it uses a variable, different variable. One is called sending window size, one is called receiving window size, one is called one variable. This is called SF, and is another variable called this is called SN. SF stands for first outstanding packet and SN stands for next outstanding packet. And there is as well as a timer, and R stands for next packet to receive. So this is the sending window. So from this given example, it is clear that the sending window can have more number of a packet or segment, and the receiver window value is set to a single packet, means it is expecting a particular packet. SF stands means what are the packet. For if this this color means it is the outstanding packet. These are the packet already been transmitted, but that not yet acknowledged. And this is the packet we can transmit but not transmitted. So once we will receive the packet, once we receive the acknowledgement, it will slide. Later we have discussed there is a concept called opening, closing and syncing later in during the TCP transport layer or TCP flow control mechanism, and this R value equal to what the packet is expecting from the sender. If it is match, it will accept it, otherwise it will discard it. That is the logic in case of what? Or go back. And the basic logic is that if it does not receive an acknowledgement, you go back to the nth position and resend it. That is the reason for which the protocol name is GBN. Go back to the nth position and retransmit it if it does not receive or it receive the acknowledgement during the RTT. So take one example, typical example of the sliding window in case of GBN is concerned. So first outstanding packet in this given example is 0. That means packet sent and acknowledged. These are the packets already sent and acknowledged, so they are forged. And these are the packet already outstanding packet, means they are sent but not acknowledged. So 0 is sent, 1 is sent, 2 is sent, 3 is sent, but they are not acknowledged. 4 other packets they can be sent when accepted from the process, and this packet they are out of the, so this is the range of the window. So if you count the number, the window size in this given example is 0 to 6 means 7. So and this packet number 7 or whatever the subsequent packets, they cannot be accepted. That is because they are outside the what is that? They are outside the window, and the sending, this is the sending window size. So these are the different variable already we discussed. First outstanding packet, next packet that can be communicated, and these are the packet already they have sent but not yet acknowledged. Okay. Now moving to the receiver size. So look at the sliding at sending window size, and now the value of SF is was 4 and SN was 0. Now if these two packets are acknowledged, then it will this window will move towards right, and now the SF will be 6 and SN will be 0. Means what? That means 4 and 5 acknowledged and forged, means they are deleted from the buffer. 6 and 7 already communicated, but that not acknowledged. So SF value changed. Outstanding packet was previously was 4, SF value now it is 6. Means 6, we are expecting the acknowledgement for 6. So acknowledgement for 6 is actually 7, because acknowledgement in this case means for the next packet it expects. So if it receives 6, receiver will send a 7. If it receives 7, receiver will send 8. 8 means here the value of M is equal to 3, 8 mod 3 is equal to 0. That is the reason, that is the logic for this. Okay. This way the sliding window slides towards the right once the acknowledgement are accepted. And now looking at the receiver, window is limited, means it is only showing one value. That means even if the sender can send multiple frames or packets, but receiver only can recognize a particular packet. So suppose sender already sent 5, 6, 7, but receiver suppose out of order 6 received first, so receiver will not accept 6, it will only waiting for the 7, 5. If 7 received, it will not accept it, it only accept for 5. So when 5 packet number 5 will be received, then only it will send the acknowledgement is equal to Rn plus 1, SCK will be Rn plus 1, that is 5 plus 1 6, acknowledgement it slide to the next value, that is Rn will now next time it will be 6. So even if 5, 6, 7 are communicated by sender, if they are reached in the out of order, so only 5 when it will receive, then only it will slide. 6 and 7 will be discarded. That is the one of the issue that is with GBN. But advantage is that in addition to the stop and wait, it has more window at center side, so utilization of channel or link is more. Now coming to the states in sending side and receiving side at GBN. In sending side, two states, ready states as well as blocking states. Ready states, what are the events that can, what are the action that can be takes place? This is related to sender. What is the first of all, request from the process comes, make a packet equal to SN, sequence number, initial sequence number that is equal to SN, store and copy and send the packet, start the timer if not running. That means when it receives the packet, and here all the packet arithmetic, all the arithmetic operations are in the modulo 2 to the m. That means m is the number of bits in the sequence number. If the m number is 2, means it is modulo 4. If number of m is equal to 3, that means it is 8. 2 to the 3 is equal to 8, means packet number will be 0 to 7, then it will be 0 to 7 again, 8 will be 0. That is the logic. If it is 4, if it is 4, the numbering will be from 0 to 15, then it will 0 to 15, like this way. That is the value of m. M is the number of bit that is in the sequence number of the packet. So what is the action when it is in the ready state? Prepare the packet, send it and return to the blocking state. So in the blocking state, same event can be done, but timeout. If there is a timeout, nothing to be done. Once again, you have to retransmit it. If you receive a corrupted acknowledgement, same thing, you retransmit it only after the your expiry of the timer. If error-free acknowledgement is received, then you will slide it. That already we explained it. In the same way, in the ready state, receiver receive the corrupted packet, discard is nothing to do. If the error-free packet with equal to Rn arrived, means you are expecting Rn and you receive a packet with value Rn and there is no error, then Rn will be Rn plus 1. Rn will be Rn plus 1, means the value of the Rn, if it is 5, now it will be 6, and the acknowledgement number will be Rn, means acknowledgement will be 6. That will see, you have to slide the window to next value and you will prepare the acknowledgement accordingly. That is the logic, simple, similar to your stop and wait, only the difference is the sending window is more. Now let's start with one example. What is the window size? this figure is related to the window size that to be maintained. This is more important because one question that can hit to anybody's mind, that if we can send more number of packet, then we can get the more benefit, because the number of window packet determine the throughput. That means also it improve the packet efficiency or channel efficiency. But there is issue, that's the reason for who is the sending window size always set like this, means the value of the sending window will be always less than the 2 to the m. So this is very commonly people are may ask you during any type of interview or any type of examination, why in GBN the size of the window is maintained, why this condition it always required. If it is not required, how the problem. Let's start with the size of the window is 2 to the m, means higher one. So let's value of m we can in this given example the value of m is equal to 2. So 2 to the 2 is 4. So window size is maintained here 4. So numbers packets are 0, 1, 2, 3, then is 0. So SM means outstanding packet. I will start with the first packet 0. SN means next packet I can start with 1. So packet 0 sent, initially it was expecting 0, received, now it is slide to next value, Rn now is equal to 1. But here assume that all the reverse channel is lossy, means all the packet loss occur when I send the acknowledgement. So it is lost, but my window size is 4, I can send more without getting the acknowledgement because my timer is running. I can send more packet. I send next 2, packet number 1, that is 2 means packet number 1, same, it slides, receive the correct packet, slide to next value 2, but acknowledgement 2 also lost, means it is expecting 2 next time, but it is in the timer is going on. So send next packet 2, it is received, appropriate packet received, slide to next value 3 and send acknowledgement 3. Now my window size is 4, I can send 4 because my timer is running. Now I receive the correct packet and I slide to next value 0. So you just imagine, now this 0 means this is the 4th packet. Actually this 0 means this 0 is nothing but your 4th packet. What the sender receiver is expecting? Receiver expecting packet 4th. But timeout event occur, means does not receive any, receiver sender does not receive any packet. So it will go back to the nth position, means it will start and retransmit from the 0. So now this 0 means the first packet or 0th packet. Now it will send the 0th packet and the receiver is expecting 0th means 4th packet, but it matches and it receives. So this is the error. What the error? Actually packet 0 means 0th packet. The expecting 4th means the values matches. So it sent old packet, but it is expecting and it is a duplicate packet, but it unknowingly accept, that is enormously accept and delivered a new data, but actually it is a old data. Duplicate packets are numbered and that is error actually. That is the reason for which we will never set the value of the sending window equal to 2 to the m, where the value of m is nothing but the sequence number. So now check, if the value of m is less than that, means it is not 4. In this case we have set is the window size is 4, now it is less than, anything less than 4 is 3, 2, whatever the case may be. So now it is 3, so 0, 3 means I can send 3 packets. I will start with the 0, I will then transmit to 1, then I will transmit 2. Same scenario, packet 0 received, slide to 1, packet 1 received, slide to 2, packet 2 received, slide to 3. Now timeout occur, means now it is expecting 3 number packet, but it will send the 0th packet. 0th packet means it will send the 0 packet, but it is expecting 3, so it will correctly discard, means it will not accept. That is the beauty of setting the value to less than 2 to the m. So that is the reason for which the sliding window always follows the sending window size should be less than equal to, or less than, not equal to, less than 2 to the m, where m is the number of bits represented in the sequence number of the packet. Now we have discussed the efficiency, what will be the efficiency or what is the different scenario. Let's start with one example. Now I think We know what is the value of SF. SF means first outstanding packet. In this case, it is 0. SM means for the next packet I can send. Initially, it is both are same. It is not communication. When I start send the packet and run the timer, I slide the SN to 1 and SF is equal to 0. Packet 0 is transmitted, correctly accepted, acknowledged 1. Packet 1 is correctly delivered, acknowledgement 2 is lost. But by the time my window size is large, I can send packet 1, packet 2, packet 3. Packet 2 delivered, I send packet number 3, packet 3 delivered, I send acknowledgement 4. So what the advantage here is, that means this packet number 2 lost does not hamper, because it is cumulative. Without go back and protocol, you just cumulative acknowledgement. So that means if within the round trip time, if you receive a packet number acknowledgement higher one, which assume that SCK4 assumes that up to packet number 4 are acknowledged, means receiver received packet number up to 4, means expecting packet number 4, that means packet 3 is acknowledged, packet 3 so acknowledged 2 means what is expecting packet 2. So this was lost. So whether packet 1 is correctly received or not, sender does not know. But once it receives packet 3, it indicates that up to packet 3 are correctly received. So this is the one of the advantage we can get in the go back N protocol, because cumulative. Cumulative means a particular loss of acknowledgement does not have any effect if the acknowledgement with higher values are received by the receiver within the time, within the that is RTT, or within that time, retransmission time. If you are receiving the acknowledgement with higher value, then we should not worry about the previous acknowledgement. That is the one of the key features of the GBN. These are the some of the scenarios explained. Better you have to go through this and you have to solve this. Let's start with example. Looking at the example, if it is let's look what the scenario is. Packet 0, you can change, look at what the when the timer runs and when it stops. Packet 0 communicated, received, acknowledged. Packet 1 is lost now. In this case, packet 1 is lost, and your window is more, means you can send more number of packet. In this example, it sent packet number 2, but what it acknowledge? It acknowledge what is that? Packet number 1 means it received. Packet number 2 does not match that with the value of RN. RN now it is showing 1. So it when it received, it sent a what is that? Acknowledgement. That means packet 2 discarded, but it expect send acknowledgement similar to what is the value it is expecting. So it is expecting 1. So it discard any value higher than 1. You can say 2, you can say 3, that will be discarded. This is one of the logic. That means any acknowledgement, any packet higher than the value of RN will be discarded by sending the acknowledgement equal to the RN value. That is that example is discussed here. Now coming to another example, packet 1 resent, because acknowledgement it received acknowledgement 1 and it sent the packet 1, and once it sent the packet 1, it sent packet 2, it sent packet 2, packet 3, and so on. This way the communication going on in case of what? In case of your go back and protocol. Now go back and protocol simplify the process at receiver. Receiver keeps the track of only one variable, that is RN, and there is no need to buffer out of order packets. This point, buffer out of order packet means no need to keep the out of order packet, they are simply discarded. You can say it is simple, but sometime it hamper the what is that efficiency. Another protocol that is called select repeat overcome this issue. That means a out of order packet cannot be discarded. So that means packet retransmission cases will be less. So that protocol, definitely it is gives better efficiency when there is a lossy channel. Means if the packet loss is occurring, then we have to retransmitting many packet, because the particular packet you are this is not accepted, then all the other previous packet will be discarded. That is one of the issue in case of GPN. Now start with what is that protocol? Select repeat. Select repeat protocol overcome this issue. Already we told. Yeah. So in simply I have told that different variable it maintained is similar to your, what is that? Similar to your similar to the GPN. It has two windows, that is called sending window and receiving window, same time or acknowledgement. What the difference is in case of windows? It the size of the window at sender at and receiver are same. Previously, sender window was 2 to the m minus what is that, 2 to the less than 2 to the m. Now this sending window as well as receiver window it will be 2 to the m minus 1. That means this sender as well as receiver window will be same, but that is reduced to half in comparison to the GPN. Now let's start more in detail. The advantage we will discuss. Let's start directly on example. This is the example. Uh, so here if you look what the size of the window here is 2 to the m minus 1. Value of m, can anybody say? It is 8. 8 means what? 2 to the m minus 1 means say the value of m here is considered as 4. 4 means 2 to the 4 minus 1. So it is equal to 2 to the 3 is equal to 8. So 8 means 0 to 7. Packet will be numbered 0 to 7. So this scenario SF in first outstanding packet 0 and 1 already communicated. These are the packet 2, 3, SN. Next packet to be sent, that is 4, 5, 6, 7. 8, 9 onwards cannot be sent. Already the same variable that is we discussed during the GPN at same. And another what the things change comparison to GPN is that receiving window, that is also same. What is that value? That is also 2 to the m minus 1 and value of m is equal to how much? 4. So it is equal to 2 to the 4 minus 1, that is equal to 2 to the 3, that is equal to 8. So that means in simple the value of Rn is equal to 3 means what? It will accept the packet with sequence number 3. But suppose it receives the packet number 4, 5, 6, 7, 8, 9, 10. It will also accept. But the value of Rn will not slide. That is the beauty. That means, but if a packet number 11 comes, it will not accept it. It will discard it. But if the packet number 4 arrives, it will accept it. It will keep in the buffer. So any packet with value higher than Rn and they are within the window, their value is in the window, they will be accepted, not discarded. This is the change. This is the change that is done in case of select repeat. And it will slides only when the Rn comes. That is the beauty of the select repeat. Now, so let's start with one example. Let assume that a sender sends 6 packets starting from 0 to 5. Receiver receives acknowledgement 3. Sender sends 0 to 5, receiver sends 3. Means what? Sends 3 means up to 0, 1, 2 acknowledged. 3 means what? Expecting 3 next time. That meaning SCK 3 means expecting 3 next time. What is the interpretation if it is GPN? GPN, if it is GPN, interpretation is that what is that? It is that means 0, 1, 2, 3 are acknowledged and it expecting packet number 3. If it is select repeat, then this is cumulative. Cumulative means up to packet number 3 are acknowledged. But if it is selective, selective means only it says that packet number 3 is required. So if the system is GPN, it means packet 0, 1, 2, 3 has been received uncorrupted and receiver is expecting packet number 3. If it is SR, it means packet 3 has been received uncorrupted, not acknowledgement 3. It means packet number 2 means acknowledge does not say anything about other packets. That means SCK3 means it is expecting 3. It is telling about the previous packet. That is the logic behind the select repeat. Now what the next thing? State uh, similar, only the difference is that size. Similar to GBN, ready state block state at sender and ready state at receiver. In the ready states, prepare the packet, send it, and reaching to the blocking state. In the blocking state, different events may occur. Timeout, if it is timeout, then it will nothing to do. Reset the timer and reset the packet. If it is received the corrupted acknowledgement, then you have to you also wait till the expiry of the timer. After that, you have to go for the same action like timeout. If you receive a error-free acknowledgement, then you have to send the what is that packets slides according to the but in receiver this is some changes in case of receiver is concerned, because window size is not 1 here, it is more. First is corrupted packet arrived, nothing, discard it. Error free packet with sequence number inside window arrived. If you are receiving a packet within inside the window, you have to keep it, but don't what is that, if duplicate, discard, otherwise store the packet. Send the acknowledgement acknowledge equal to sequence number if the sequence number is equal to rn. Deliver the packet and all consecutive packets arrived and stored. That means what? That means you will send the acknowledgement as per the rn value. If you are receiving the rn value, then only you have to slide. That is the logic. Next, it will be clear by discussing through one example. Let's start with an example. Let's go. Packet 0 received. Waiting for what? What is that? Waiting for packet number 1. It is not 0. It is packet number 1. Waiting for packet number 1. Packet 1 lost. Window size is more. Send packet 1, packet 2. SCK2 means what? Expecting packet number 1. So packet 3. So this way similar to the GPN, but only change is that it will keep any packet other than RN value if their value is inside the window. It will not keep any value outside the window. So now the window size that is judiciously selected, already I have told the sending and receiving window value will be set equal to 2 to the m minus 1. So if it is greater than 2 to the m, let's start with an example. And here m value is equal to how much? 2 to the 2. So m value is equal to here considered as 2. 2 means what? 2 to the 2 minus 1 means 2 to the 1. 2 to the 2 greater than 2 means 3. So the value of m is equal to 2. 2 to the 2 minus 1 is equal to 2. Greater than 2 means anything value greater than 2 is equal to 3. So here window size is equal to 3. Packet 0, 1, 2 I can send. Packet 0 lossy channel, lost. Packet 1 lost, packet 2 lost. But their values RN value matches slides to its rights. So initially it was 0, slides to 1, slide to 2, slides to 3. Now window size RN value is 3, but it can also expect receive 0 and 1. So timeout event occur, it will resend all the packets starting from 0. So when it transmits 0, it is actually which packet? Packet 0. But this value is also there, but this is packet 4th. So it enormously accept the packet. So that the problem associated if the window size is greater than 2 to the m. So you just imagine you can have to understood the problem. If the window size is greater than this, then we will enormously we will accept the packet even if it is a duplicate packet. But you just go through this. If it is less equal to that value means equal to what? We keep it not 3, we keep it 2. If it is 2, just packet 0, now it is 1, packet 1, now it is 2, now it is timeout event occur, it will resend 0. So in this case, what is the window size? What is the value it is expecting 2 and 3, packet 0, discard it. That means it knows that is expecting 2 and 3, but it is set 0, it will discard it. Already it is received. So that is the correctly discarding the old packet. So this is the reason for which the select repeat protocol determine or set the window size equal to 2 to the m minus 1. Now quickly bidirectional protocol we will not discuss. So this is the overall description of the selective repeat protocol. Let me to conclude here about flow control mechanism. We discussed about the three protocol. One is called stop and wait. We discussed about GBN. We discussed about select repeat. The advantage of each one is stop and wait is simple among all these three flow control mechanism with window value is 1. Simplest among all. GBN, but the problem is that channel utilization is less because packet size is 1. GPN is very popular or improves this performance by improving the sending window size to higher one. The window size will be 2 to the m minus 1, means 2 to the m minus 1 means almost 2 to the m, but in case of selective repeat is reduced to half, means 2 to the power minus 2 minus 1. So but the problem in case of GPN is that any packet whose value not matches with RN will be discarded. Subsequent packet, out of order packet you can say, that is one of the limitation in case of GBN. Otherwise GBN have good channel utilization. Now coming to the most popular protocol, that is very popular, select repeat, which overcome the issue by increasing the window size in the sending as well as not increasing the receiver window size, by increasing the by increasing the receiver window size, not the center window size. Actually the window size here is reduced in comparison to GBN, but the advantage is that out of order packet can not be discarded, they can be stored, they can be in the buffer, so that the number of packet retransmission is definitely minimized. So this is the different flow error and flow and error control mechanism that transport layer uses. So next we will discuss the protocols. In the next video we will discuss the transport layer protocols, then we will discuss UDP, we will discuss TCP, and we will discuss how the functionality, packet header, all this information, and how TCP also, how TCP flow control, that is which type of flow control mechanism TCP uses. So let's stop the video at this time. So next video will focus on other part of the this transport layer.